Hello, calculus fans. Okay, so now we're interested in trying to compute derivatives of sine and cosine, and then later we'll work on the other trig functions. And so that's what we're going to try to do now. If you were to take a look at the graphs of sine and cosine, it would actually be pretty reasonable to think that the derivative of sine is cosine. And actually the book has a demonstration with the pictures of sine and cosine so that you can see this. So what we're going to do is use the definition of the derivative to try to see how this might play out. Now before we go ahead and compute the derivative of sine, there's a couple of trig identities from pre-calculus that I want to show you. These should be familiar. You will have seen these before. So these are the sum angle formulas for sine and cosine. In fact, I always say that there's only 3 trig identities that I know. There's the usual Pythagorean identity, which says that sine squared theta plus cosine squared theta equals 1. That's one of the 3 trig identities I know. The other 2 are the sum angle formula for sine and cosine that you see here. Every other trig identity can be derived using these 3 trig identities. So I really just keep those 3 in mind. So now let's use these 2 trig identities along with the limit definition of the derivative to compute the derivative of sine x. Alright, so we want the derivative of sine x, so we'll use the usual thing that we've been doing all along, which is to put it in the limit definition of the derivative. So the limit as h goes to 0 of sine of x plus h minus sine of x all over h. At this point, what we're going to do is use the sum angle formula as applied to this piece to try to simplify this expression. So if you go back into this sum angle formula that we're using for sine, I suppose you could think of A as being x and B as being h, and then you should be able to see that this portion here comes from the sum angle formula as applied to this expression here. So you should see how that works out. And now I'll do a little bit of rearranging here just to break it up into a couple of fractions, and you'll see why in a moment why I'm doing this. Essentially the idea is I want to get the cosine h and the sine h in 2 separate fractions. Okay, so now let's see what happened here. Notice that up here you can factor out sine x, and that's where you see here. And then of course on this fraction it's not really factoring, you can just move this cosine out in front here. Now we apply a bunch of the limit laws, where we can break these up into a whole bunch of different limits, just because the limit of a sum is the sum of the limit, and same thing with products. This is, of course, assuming that all of these limits exist. They may or may not exist. Now notice that we're taking a limit as h approaches 0. So for instance, this limit here, that's just sine of x, because it's a limit as h goes to 0, and as far as h is concerned, sine of x is just a constant. And the same thing happens here. So we're just using the limit law that says the limit of a constant is that constant. Now sine of x is not a constant, but in terms of h, it is. If you were to change the value of h, then sine of x doesn't change. So then all we're left with is we need to figure out what's going on with this limit and with this limit here. Okay, so we need to figure out what's going on with the limit as h goes to 0 of cosine h minus 1 all over h, and the limit as h goes to 0 of sine h over h. Now I'm not actually going to show you the proof here that these limits exist, but the book has a nice geometric argument. So for one of them, the book will use a trigonometric argument, the other one uses the squeeze theorem. What you should at least do to convince yourself that it's reasonable to think that these limits exist is to just plug in some small values of h and see what you get. Now when you do this, make sure that your calculator is set to radians. If you don't have it set to radians, if you have it set in degrees, you're not going to get the right value for the limit. In fact, you might even try this. Set your calculator to degree mode and try to check these limits. You won't get the right thing. So as I said, the book actually proves this. The book proves that the limit as h goes to 0 of cosine of h minus 1 over h is equal to 0, and the limit as h goes to 0 of sine h over h is equal to 1. Now, if you don't use radians, you'll still get 0 on this one, but you wouldn't get 0 on this limit. I think this is actually worth trying out, just plugging in some small values of h and seeing what you get. Okay, so let's go ahead and move on with these values of the limit. Now, if you're interested in the proof, you can go look in the book and see how they do that calculation. If not, you should at the very least plug in some small values of h and convince yourself that this limit, both of these limits, come out to what the book says they do. So if we go back and remember what we're doing here, we're trying to compute a derivative of sine x. If we plug everything in to this limit, let's see what we get. So remember, this piece here is 0 and this piece here is 1. So we'll end up with sine of x times 0 plus cosine of x times 1. So clearly the sine of x times 0 just disappears, and we're left with cosine of x. So again, remember what we're doing here. We're computing the derivative of sine of x. And as long as we believe the value of these limits, then we've proven that the derivative of sine of x is equal to cosine of x. And as it turns out, you can use a similar approach and still using these limits, you can prove that the derivative of cosine of x is equal to negative sine x. And actually this is going to be one of the homework problems to do a similar kind of calculation to prove this. Okay, that's all for now.